actually start coding a feed-forward neural network.
So in this tutorial, we will be going over our first neural network implementation. This isn't truly a neural network per se, because there isn't a hidden layer that we're going to be using. There's just an input layer and an output layer. But the problem we're trying to solve is the one that we went over in video 3. Given a set of inputs and outputs, create a neural network to predict the outputs given the inputs. And these are the outputs and these are the inputs. And so we've created a black box here. We went through all of that and then we said this was our first neural network. And so what we'll be doing is we're going to be taking this black box diagram and we're going to be implementing it in our code. And so what you'll recognize is that it's the same technique that we used when we implemented the sigmoid function backpropagation activation functions in the previous video. So we're going to create a class and we're going to call it net. We're going to define it with 3 inputs, x1, x2, and x3. We're going to have a step size for our updates to our weights that we're going to do later. So when we have our synapse weights, we're going to need that because there are updates that we need to do to our synapse values later on, and we'll talk about that. And then, yeah, so these are the step sizes, right? So we need that step size in our function. We have our expected. That's the value that we want, right? That's our expected output right here. But that might not be the output that we get initially, right? And that's our expected. Here are the randomly seeded values for the synapses. And we talked about the synapses before as being important, right? So we said seeding a neural network means deciding what the starting synapse weights are. And so these are just randomly defined from -1 to 1 for now. And we're going to have a thing for the derivatives for those synapses, right? And so, because we're going to be updating the synapses with these derivatives. We're going to have an output, and the output is whatever we get out of this. It's not the expected output, it is the output, right? And then we have the derivative of the output. So we have all our derivatives, we have our inputs, we have our outputs, we have our synapses. Here's how we're going to activate this thing. We're going to do our multiplications for x1 and A, x2 and B, x3 and C. And then we're going to activate all of those. So what we've done is we've done x1 times A, x2 times B, x3 times C. And we activated it so all these wires now have values here. All these wires after the multiplication have values now. Once we've activated it, we've done an add block. It's a 3 add block, so it takes 3 inputs, and we set that equal to the outputs of the multiply function. So this is the outputs of the multiply function. We set those as the inputs of the addition block right here. And then we activated it. So that now this little tiny wire here in the middle actually has a value. It's the value of all these added together. x1 times A plus x2 times B plus x3 times C. And the wire here has that value here. Alright, and then we're going to set that input of the sigmoid function, the output of the add block. y1 is the output of the add block. And then we're going to activate that. And then now we have our output here as we see it. And so we're going to set that output of the sigmoid block as the output of the entire feed-forward neural network. And that is how we activate it going forward. How do we backpropagate? Well, we're going to use the same technique we did with the sigmoid function. We're going to take an error, and see that's the thing. Our error is going to be the d out, and we're going to define that later. But our error is going to be the d out, and then we're going to propagate that error throughout. So we have a derivative here of the sigmoid function, and so we're going to take that, we're going to backpropagate it here, and then that when we say backpropagate the sigmoid function, we set this wire value to be this derivative. We take that wire value here, and then we set that to the input of the addition block right here, right? And then we backpropagate that, right? And then so now all these 3 wires have values. So we've done that. And then we backpropagate the multiplication gate. So the multiplication for the 1 is the derivative of dx1, which is here. And so we have the values for A and for x1, which we'll just throw out later. We have the values for x2, right? So that's our center one right there, which is B and x2. And we have our values for x3. And so we've backpropagated and we have our values here. So all our derivatives are here. And so we're going to set those derivatives to dA, dB, and dC. So that's what we have here. We have the derivative of dA, we have the derivative of dB, and we have the derivative of dC. So we have our derivatives and we have our forward propagations. How do we train it? Well, first we're going to have to activate it, which means we're going to go here and we're going to have our inputs, we're going to go all the way through, and we're going to get an output. We're going to take our output, right here, and we're going to subtract it from our expected. So expected minus our output is going to equal D out. That's our error. So if we expect 80 and then our output is 100, then we get negative 20 as our D out value. Now that we've set our D out value is what our backpropagation function takes in, right? So that's our D out value, which is kind of the error or the derivative. Then we're going to backpropagate that. And once we backpropagate it, we have our derivatives for dA, dB, and dC, which are the derivatives for those synapses. We're going to now multiply by the step size and add by the synapse. And then now we're updating our synapse values. And this is how we train once. That's how backpropagation works. So this is a very beautiful sort of function that allows us to do that. So here's our test set from the problem that we've had before, right, in our slide that we covered in video 3. Our inputs 0, 0, 1, 1, 1, 1, 1, 0, 1, 0, 1, 1. Same inputs right here, same outputs right here, and then what we're going to do is we're going to say, all right, this is what we're going to train our neural net on. How do we do that? Well, we create a neural net, and then all I'm doing here is printing out the values of the synapses before the training. I'm running it through and activating the net before we've trained it. So 0, 0, 1 is equal to 0, right? That's our expected. We activate it. Also, we're going to do 1, 1, 1. Our expected is 1. So we just go through and we set our inputs and we set our expected outputs and we activate it. And I'm just printing out those values. And you can see that those values will not match. Then now we're going to train 10,000 times, basically using backpropagation. We're going to set 0, 0, 1, and then we're expected is 0. And we're going to train once on that, so we're going to say, all right, train on this. We're going to set it to this, and then we're going to train once for that expected output. We're going to set it to this, train once, and set it to that output. We're going to set the fourth one, set it, train it to the output. And then essentially what we're doing is something called batch training. So we're essentially training all our data at once. And so it'll print out these values after I set it to 777, so our console output is not like super filled with just like random values, but essentially it'll go through and it'll set the synapse values every 777 times. Let me just put that to 1,000. So every 1,000 times it'll print out the synapse values, and we're going to see those updated. And then we're going to do the same thing that we did for displaying the synapse weights after, and then test it again later. So take a look at that code. I know I went a little quickly, but I wanted to show you the output of this neural net now that we have it all built and trained out. So here it is, Python neural net 1. It'll train it. So before, you can see that these are our synapse weights. And then the values didn't match. 0 is not equal to 0.7. 1 is not equal to 0.89. I mean, it kind of is, but it's not close enough. And then we'll just say, you see the values don't really match. And then so that's cool. And then the synapses are being updated, and you can see the synapse weights changing pretty significantly. A is increasing because A plays a significant role in determining the output for the synapse weights, while the rest of them are decreasing. And so what did we say? At the end, A is the biggest value there. So you can see it still has a ways to go in the training. Sometimes it doesn't work as well, right? But at the end, you have a value that's pretty close to 0. You have a value that's pretty close to 1. You have a value that's pretty close to 1 here as well. And you have a value that's pretty close to 0 here. And if I showed you, we can actually train it a little bit more using 100,000 times, and it should essentially converge. So that's essentially what I'm going to show you in this video. You have created your first neural network. And the code to this should be at the end, linked in the description. And as you can see, the more times we train it, the better it gets. And we're going to have to be careful because we might have something called overfitting the data. We'll talk about that later. But essentially, you've trained your first neural network. So that's how neural nets work. In the next video, we're going to be talking about more complicated neural networks with a hidden layer. And if you understand that and you're able to add more hidden layers and create very complicated feed-forward neural networks. Thank you.
Classification.